Paul here. Today we have on the bench a monstrosity. This is a 13 tube radio, actually 12 tube plus a magic eye tube, so 13 tubes. And it's a Silvertone, and we're gonna get it going. I'll give you a view of the chassis here. Huge 4-ganged capacitor, tuning capacitor. Has 4 bands. Has the AM band for the AM radio, which is A. The B band is 1.5 to 4.2 megs. Has a C band of 4.5 to 9.5 meg. And then it has a D band that goes from just under, well, about 8 meg to 19 meg. So it's an awesome radio, and it's huge. And look at the size of that transformer. That's a skyscraper of transformers. It's got one on the top and cores all over the place, so it's huge. And the tubes are in really nice looking shape. So I'm going to turn it around. We'll get the model number, and then I know somebody's worked on it because this is not the original potentiometer here. I don't know what this is. It's brass bolted to the chassis, but this is an aluminum shaft, and they didn't use aluminum back then. They had brass or steel. But this one is aluminum, and somebody had ground slots in it, I guess, to get a knob on it. I haven't seen the knobs just come out of a console. Here's the speaker for it. Huge speaker, big 12-inch speaker, giant field coil in there. And look at the size of the output transformer. They're beefy radio. So let me turn it around. We'll try to figure out the model number, and then we'll flip it up on this side, and so we don't hurt any of the tubes, and the transformer should be okay to hold it. And we'll look at underneath and see what's been done to it. Before I do that, let me show you this thing. I don't know how in the world this works. It has copper tubing going into these IF cans here, and it has a wire going through it, so it's like a brake cable on a bicycle. And those wires are pulled up and down by this shaft, which pulls something up and down mechanically inside of the IF cans. That's just, that's Frankenstein there. I mean, this thing here I think could raise the dead. Anyway, let me turn it around and we'll continue. Okay, here's the back of the radio. We have a label there which has some information on jumper wires and how to connect an outside antenna to this device, which is for the outside antennas. And then we have the label that has the tube layout, so 2, 4, 6, 8, 10, 12, and then of course the magic eye. Unreal. And this is the location of the tubes viewed from the rear of the cabinet, the way we are now. And the model number is hard to read. It looks like 196S. I don't know if you can see that right there. The camera will focus. It's not going to focus on it. There we go. It could be 1965, but it looks like 196 and possibly a 5 or an S. I'll have to find the schematic on it. Then we have the serial number, which is partly tore off, and then these are all of the patent numbers for the U.S. patents. It's got some marketing lingo here. No radio is stronger than its weakest tube. I like it. I think I'll make that my slogan. For best results, use super Silvertone tubes. And then it has the RMA member sticker on it. This model is approved by the Engineering and Institution. Engineering Institute, RMA member. And over here we have the speaker jack, and I don't know what the 318X means, but that must be the plug. 25 cycle or 25 hertz RS. So that would be, I don't know, it's interesting. A little bit of popcorn there from packaging. Okay, so I'm going to flip it up and we'll look underneath. I know some work has been done. I haven't seen the bottom. You're seeing it just like me. I just now set it on the bench. So we'll look at it together. Let me turn it on its transformer there and make sure it's safe, and then we'll take a look underneath. Okay, and here's the bottom. And we'll start up here at the top. What we see is one filter capacitor changed here. That's this one. So it has been replaced with a MIEC, and they didn't do a very good job of tying it down. Something's fallen off of it. I don't know what that was. And it is a 16 microfarad at 500 volts. Of course, I'll verify that when I look at the can. We have all the original waxies. They got to go. Looks like somebody replaced the power resistor up here. And they had it leaning on that, oh, that's another resistor there, power resistor, the original one, and they jump it over part of it with this one. So maybe that part of this wire wound original resistor was bad, and so they jumped it with a new resistor, which is fine. We'll check it out, make sure it's correct. We'll check out the values of these dog bone resistors as we go. And in case you forgot how to read them or haven't figured that out yet, for those of you who don't know, a dog bone resistor, the easiest way to remember how to read the resistor value on dog bone resistors is to use the acronym BED, B-E-D, and that stands for body and dot. So for this one, the body would be 2 because it's red. The end is black, so it's 2, 0, and orange is 4. So orange is 3. Sorry, orange is 3. So this is 20K. Here we have yellow, black, black. So that one is very low resistance. That one is 400, 400 ohms. There's another one. This one is 401. So that's what that is. I'm sorry, that's a brown dot on both. I failed to mention that, but it's 400 ohm. So it's yellow, black, brown, yellow, black. Here we have another capacitor that was replaced. It's a 400 ohm. And put in the circuit, and that is not a very good solder joint there. We'll tighten that up. But this is a Sprague 0.01 at 600 volts. We'll be replacing that anyway. Here's another capacitor that was replaced. I'm not sure which electrolytic this is. I'm assuming it's this one. No, maybe not. There's 2 more here. So I don't know what this one is. It goes to ground and it connects. That really makes very little sense. It looks like it's going, oh, this capacitor is insulated. Okay. So it's across 2 filter capacitors that are insulated from the chassis. Again, like I said, I'll get the schematic, we'll check that out. Look at this interesting capacitor. That is just really cool. I love the design on that. Let's see if we can see that better. Yeah, that's better. You see that that's just really cool. I've never seen a logo like that. It looks better on through my eyes than it does through the camera. It's got like a B, a CB in the middle, and then those lines on the left and right, it's like a horseshoe going underneath the letters. Those are actual lines, not a black band like on left and right there. And then it said something on it. That's an interesting looking capacitor. I've never seen one of that. Here we got some resistors on a power strip board, heavy duty. It has some capacitors there. And of course this is the bottom of that big hefty transformer. Has a coil resistor here, which actually extends beyond the box out this way. That might need some attention, but we'll look at it and measure it and see what we got. So all this needs to be verified. Here we have a tag of somebody who worked on it at one point, most likely. Doesn't say anything on it. It looks like a last name. Probably the owner, the technician put that on there so he would know who it belonged to. But that's old. That tag is definitely 40s, 50s style tag. And it's tied on with a piece of thread. Can't read the name. Winter, maybe? I don't know. F-U-N-T-E-R-T, something like that. And these are the braces for the transformer. And this thing is huge. Another power resistor here that was added on. So apparently this wire wound resistor has gone bad. And so somebody in the distant past tacked this one, which goes from here to here. It's a power divider, a voltage divider circuit. And then somebody else, more recently, put a newer, we'll check these two and make sure they're right. Mount brackets, those are riveted on, so can't take them off unless I absolutely have to, and then bolt them back on, but I'd rather not, or rivet them back on. I'd rather not do that. Is inside of the tuning coils. It's in the back there. And then we have all of these coils, which are the frequency coils for the different bands. And this is the band selection area. So this shaft here goes right through and changes all of these wafer switches synchronized. They all turn together and it tunes all the different bands uniformly. That's in addition to the 4-gang capacitor on the top, which does the same thing. These are the coils, and on the top you have the capacitors, so your inductors and your capacitors. And you can see how the end of these capacitors has opened up and the wax has started bleeding out. This one got pitted, which is really strange. That's just really strange. That's kind of normal damage, and this one hasn't leaked yet. And I would imagine that that's from heat, and they're standing, when this chassis is laying down, they're standing vertical, so the pressure of the melted wax, the tendency of the hot melted wax would be to run down this way. Imagine the top end, it would be countersunk. Like this one is kind of still in good shape, still kind of countersunk. But as are these. You see, gravity might have made that one swell down, see, but that one there still looks nice. Of course, these capacitors are a disaster waiting for a place to happen, so they got to be changed. So we're going to work on it. The first thing I need to do is check all the coils, make sure I have continuity in all of these coils. Make sure everything is working before we put any time into it. The second thing would be to check all the tubes, make sure they're all good and functioning correctly. And then before I even power it up, I need to get a schematic and verify these capacitors are correct that were replaced, and check them to make sure they're still good. This yellow one, I'll probably just switch it out before I power it up at all. And then we can bring it up slowly on the variac with a current limiting bulb to see if we get anything out of it. And then we'll know, of course, that all of these capacitors will need to be changed. So I'll probably skip that step and just change them all. Or we might go ahead and do a trial run and just see if it actually picks up anything before we go changing all the wax capacitors. They're all going to go, so it doesn't matter what order I do it in. It'd just be interesting to see how the Silvertone is holding on with its original wax caps in place. Of course, we would not let it draw any current because we wouldn't want to hurt anything, but just to see how it's doing. I wouldn't be surprised if it fired right up. Most of these antique radios do, unless there's an actual short, in which case that's what the current limiting bulb's for. It won't let the unit draw more current than needed, and of course, with eyes on, you shut it off right away if the current gets too high. So anyway, that's the next step. I have to validate all these coils. While I got it up like this, I'll go ahead and do that. Check all of the coils that I can get to here. And then we'll check the IF cans where the wires go through there. We can trace the IF cans back and check them. Probably go ahead and find a schematic to aid in doing that. Okay, so I set up the camera. Thanks for watching. We will continue what I'm doing. I don't think I can get the meter in the shot here. Maybe. It's kind of hard to get the meter in the shot, and you see what I'm doing. I have to be far away because of the length, but you just have to bear with me as I read out the values to you. First thing I want to do is check this resistive assembly and see if we got continuity going through there. So I'm going to go across each resistor section that they put in here, and the first one is 25.8 ohms. So we need to verify what that is. This one is reading roughly 1.47 ohms, k ohms. So 1478 is what it's reading. All right, this one here is reading charging a capacitor. It's over 2 megs. So we got a problem here because this little bit of coil cannot be no 2 megs. So I think this one is open. I'm getting, well now I'm just under a meg, but it's counting down because it's charging a capacitor that's over it. It shouldn't be charging a capacitor. This should be less than a meg. So I don't know what it really is, but I'll go back to the first one again. I said it was 25. Yeah, 26 ohms. So this is a low end coil. From here to here, it's 26 ohms. From here to here, we got k ohms, 1,000 ohms, and we're reading. I'm not getting a connection on that solder joint. 1479, and here we're getting nothing. It's just charging the capacitor up, it's just climbing up. If I turn the probes around, it'll be climbing down. Yep, it's back in the mega ohms and climbing down. So this part of the resistor is now open, which makes sense. These were changed quite a ways back, and if this thing was deteriorating over time, which it obviously was, because this one is an older style than this one, so I would imagine they've been replaced at different dates. This center went out, they put this one in, this one went out, they put this one in, now this one's out. And that just makes sense. I don't know if there's a value on here I can read. I don't see one. It might have got hot. And it might be the wrong value. This one says 25 ohms, 10%. So, and I think I had 26 on it, so it should be still within tolerance. Just doesn't want to make good connection on that. Yeah, the 26 ohm. It's 25 ohm, 10%, so it would be plus or minus 2.5, and we're within that tolerance. Okay, the next thing we're going to check, I just want to work down while you can see up high. We'll do these, and pardon my hands as I reach in here because I can't see the camera at the same time. Here we have a 401 or 400 ohm resistor, dog bone, and we're getting 417. So with a 20% tolerance, that's good up to 500 ohms. So that one's fine. Most dog bone resistors are fine. Here we have a, not sure, that looks tan, and that don't make sense. It's probably, I don't know, let's measure it and see what we come out with and then decide if it makes sense. Okay, I'm getting 120 ohms on it. So if it was brown, black, brown, it'd be 100, and 10% would be 110. So that would make sense that that's what it is. And getting 100 and again, I'm not making great contact. Oh, it's climbing. Okay, it's stopping. So I'm probably charging a capacitor in the actual tube. I probably should have the tube out. But, and I was about to say, I'm getting 122 ohms. It's good from 90 to 110. It's probably capacitance, well, not capacitance, but internal resistance in the tube that's driving this up. I bet if I disconnected it, I'd probably be within tolerance. And even if it's a 10 out of tolerance, for the amount of years this has been in here, that ain't no big deal. It'd be fine. So I'm not going to worry about these resistors unless they're like open or shorted or way out. I think this is another one. This one is registering 114K. 114,000. We got brown, black, yellow, which would be 100,000. So 114 is just barely over 10%, and these are 20% resistors. So again, fine. That one's definitely in tolerance. This one's a little out. This one here is a 2K, 200 rather. I'm sorry. Red, black, brown, yeah. 200 ohms. Okay, I'm getting, that one's got a problem. I'm sorry, it's the other way around. It's a 1K, duh. It's my brain is concentrating on trying to get the probes on. I'm not really looking at the color right. So it's 1,000, and I'm getting, once I get the thing probes to make contact, they're not doing it. Old solder joints are hard to connect to without something to help. Okay, I'm getting 1,083, so it's good up to 1,100. It's good up to 1,200, so we're fine. That's great. This one here, I assume I'm still in the camera length, which is green, black, orange, or 50K. I'm getting 62K on it, so that one's out of tolerance. It's up to 12 over. Again, it could be if I desoldered it, it might be close, but I'll flag that one to be checked. All right, let's continue on. Did I do this one? Not sure. I think I did. Need to keep my mind on what I'm doing. Yeah, 32K, and it's rated at 200K, I mean 20K. So that one is suspect. That's two that I'll probably pull one end off and check. This one here, 416K, which is about right. It should be 400K, so it's within tolerance. Okay, that's those. Let's see. Again, I'm really concerned with shorted resistors more than anything else. Open resistors are not good. They'll cut the signal, overdrive something. Okay, this one is brown, black, green. I'm getting 2.6 megs, and it's a 1 meg, so it's definitely got to be changed. Yep, I'm getting 2.6 megs. That guy's bad, so he's got to go. What else we got? We got this dog bone here, which I can't see the color code on, so we'll probably need a schematic to verify it. 1.2K, and I'm thinking that is a red dot that I'm seeing right there, just underneath. So if that is a red dot, that would be 2K, red, black, brown. That wouldn't be 2K, it would be 200. Check that again. Oh, no. I did it again. Brown, black, red, it'd be 1K, so yes, it would be out of tolerance and need to be replaced, and it's hiding there nice and neat, like you're not going to know it's there. And I'm not thinking that that goes across any of this, so I can't really tell where the other side of that goes without laying this down, and I'm not doing that right now. Again, I'll check these continually while I'm changing capacitors, while we're troubleshooting the circuit. Right now I'm more interested in coils, but I figured since we're starting at the top, I might as well let you see how that goes. Testing them in circuit, 90% of the time will give you the right value. Some of the times it won't, depending on what's connected to it. It could be a resistor somewhere in the circuit that's across it. This one is 500 ohms. I'm sorry, 1 meg ohm. Brown, black, green, 1 meg ohm. And I'm getting 1.12 meg, so it's fine. Here we have an orange, green, black, orange, so this would be a 10 meg. No, I'm sorry, 10K. Get in there. 100K. It would be something, right? I'm getting a reading on it though. Come on. Alright, it's across the capacitor. Yeah, let's stop. 53.8. Body's green, that's 5. 5. Orange, that should be 5K. Try it one more time. 53K. What am I doing now? It's not yellow. Orange, so it's 3 zeros, 4 zeros. 50K. Yep, okay, it's fine. It's a little out of tolerance. I see. Okay. Well, that takes us to the coils. So let me zoom down here a little bit. I think you were pretty close. Okay. A little more maybe. Drop this down just a little. Alright, we're going to check these 6 coils. Now here all I care about is continuity, so I don't need to worry about the values. I mean, some of them are center tapped, but... Alright, so we'll start with this one here. There's 2 terminals side by side in here. They're probably connected together. Yep. Okay, they're fine. And there's 2 side by side down here. They're fine. And that's it on that coil. It doesn't have a top tap. And this one does. You see it there. So we got 2 side by side down there. Fine. And that probably goes to here. I can get it to connect. Alright, so it goes here. And the other one is probably, it's got to be connected to it, yeah. Okay, and then on the bottom we have another coil in there. Here, it doesn't have a center tap. And yeah, I basically touched it for a second. There it is. Okay, that coil's good. Let's try this one. That's good, and this is a center tap for it. I believe it's center tap, but let's see. This. Alright, this is 0.4. The whole thing is 0.8, so yes, this is a center tap for that. It could have been the other way around. I mean, could have been from here to here, and that could have been a center tap, or here to here, and that one could have been a center tap. It's good to know where the center tap is, because which in this case, from here to here is the coil, and this is the center tap. If I check from here to here, and I get continuity, I know there's continuity here, 90% of the chance, 99% chance, because that goes a coil up to here and then coils back down to there. So if I have continuity across the two ends, then obviously the middle's got continuity. However, that's not always the case, so you want to check, because this solder joint could be broken. The coil may go completely across and back down to the other side, but the connection here where it's connected to the coil could be broke. Now that's very rare, but it can happen, and it'll drive you nuts if you don't check it, and it's that way, and you can't get it to tune, and you're spending hours trying to figure out what's wrong with it, and all the time it's a coil you already checked. So when you're working on these coils, if there's a center tap, check it to the center tap. Make sure that you have a good connection. Oh, by the way, here's another one of those cool flax capacitors with the logo on them. I really like that. But you'll get to look at it close to
the wire on it, so it's probably not used. Okay. That may only be up to here.
Next
Yeah. That may not be used. Let's see, let's try two other terminals. Either here maybe? No. Let's find the two that are used. Okay, that's used. They're using half of this coil. There's the other half. Here, do they have a wire on that? Yeah, they have a wire on it. I think they're just using that one as a tie point. Judging by the coil, the number of turns, you can't see it. But on this, I see the two. Huh? Judging by the number of turns, it has a lot less turns. It may be that this joker here is not being used, and not that it's bad. It does have a wire going to it, but it could just be a floating connection, because it's not going anything else, not going to ground. I have to check that. It's coming off this terminal here, and it's got this wire that's going to there, and it's got a resistor that goes, this dog bone that goes here. So it may be just a tie point. Since this one doesn't have a wire, it may be they're just using this as a tie point for this resistor going to here. Basically, this resistor goes from here to here, and you've got it tied with a wire going through the case here. That make sense? Okay, I think it does. All right, so let's check that resistor. If we can't, once it's over here. But we can check here, let's see. Yeah, we can check it here, 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 and here. And then we're getting connected to it, I don't think. Oh wait, yeah, that's there. That's there to there. On the other side of that, looks like it goes here. And I'm not getting, oh, wait a minute. Can't do that on continuity because it only measures up to a certain resistance. Okay, there we go. It's 130K, and so that should have a yellow dot, and it does. Brown, black, yellow, 130K. And it's supposed to be 100K. So it's out of tolerance, but again, it could be, these coils could be, no, I'm jumping across it, they shouldn't be connected together, but it's possible. So it could be something in circuit from the other side of the resistor. See, there's a wire that goes through here, goes through the coil, it could come through another wire, go around and go through other components and come back to here, in which case it'd be across that resistor, whatever the other resistance is, which could, well, no, I shouldn't drive it up, I should drive it down. So that's bad. That one's out of tolerance, yeah. Out of tolerance, shouldn't be more than 120K max. So that one's got to be changed. All right, let's continue. Oh, we were on this coil next. Back to continuity. Okay. So that's fine. Here to the center tap, fine. Center tap to down there, fine. Across it, it's fine. Okay. We have these capacitors. I can at least check to see if they're shorted, but I'm not going to get nothing that way. It's not really going to tell me anything. It's only going to tell me if it's shorted, it'll tell me they're shorted. I don't think they're shorted, they're just no good. No, they're not shorted. Okay, and I could check them that way, but I'm changing them, so there's no sense in that. Okay, let's see. The same, now the micas usually stay, they don't usually short, so you can check those, and they don't need to be changed unless they are shorted. And they're fine. What else can I tell you here? Nothing. Other than I am checking it with the tubes still in the sockets. If I was really concerned with checking resistances, like I said, I'm mostly looking for opens and shorts. But if I was really concerned with checking values, especially on tube sockets or the go-to tube sockets, I would pull the tube. That way there's less chance that
it goes somewhere else. Now, it shouldn't go through the tube unless it's connected to the filament. That's the only way you have a direct connection through the tube. Or, if the tube is shorted, then you could have a direct connection through the tube, which would give you show you a short on the resistor, or an intermittent short. We might show half the value of the resistor, when in reality the resistor is still good. 90% of the time, checking them in circuit is fine, even leaving the tubes in. You'll know when you check a tube if you got a bad tube. If you got a bad tube, then you're going to want to check all the way around it to see what might have caused the tube to go bad. So anyway, continuing. Here we have a 1 meg. I think we did this one, but let's do it again. Gotta get back on. Ohms. And it's perfect. So it's fine. Here we have another such tube. This one is a 100K. I think we checked it right. It was 111. Oh, I'm sorry. There's the 50, the green, body green. I'm so used to a carbon resistance. 53K, and that's what it is. Green, black, and 30 to be 50K. All right. Now we are down past this area here. I don't see anything else. So we have this resistor that was put in. We can check it for a short. No, it's fine. Okay. Now we're going down toward the transformer, so I'm going to have to bother the camera again. Just bear with me. Okay. There's the transformer. If I go above the transformer when I do those resistors, I'll come back up. Get down. We'll just do the transformer for now. Okay. This funky one. Let's go across it. Okay. That coil's fine. This coil's fine. This looks like it. And that's just an input wire for the coil, and that's the other side of it. This is the line cord input. So that's the primary of the transformer. It's fine. This, I believe, is just ground. Yep. So the next one. Okay, it's fine. Now, see this resistor, the way this looks? You got a metal bracket, a coil of wire around a piece of an insulator, another metal bracket coming out at a 90 degree, which is a center tap off the whole thing, another coil of wire around an insulator, and another metal bracket. Okay, so if we go across the whole thing, we're checking across the resistor and the coil. Now the resistor could be, say it's 100 ohms, well the coil is only going to be 0.4, 0.5, so you're not even going to see that. But when you go here to the center tap, I got to get back to regular ohms because it's obviously over the limit there. Okay. I'm getting 13 ohms from here to here. That tells me that this half of the coil of the resistor is good. Now I can come here and do the same thing, and it's going to give me somewhere around the same, I would imagine. Yeah, 12.6 ohms. So this half. So we just checked that resistor in circuit. Even though it's a much higher value, it's 50 ohms, and this is only less than an ohm, we just checked this resistor without this making it impossible to check it by using the center tap. All that said is what we have here, and here we have a problem. We have a problem for twofold, or a couple-fold. One, we have a problem because the center tap is not straight out at 90 degrees, which means there's some issue there. But we already know what the issue is because we can see it here. We have the missing insulator that went through the coil, like on here, here, and here. The insulator's missing. All we have is the coil, and so we have this coil wire here dangling in free space. Whether or not it's connected here or not remains to be seen, but it's not wrapped around its coil, its centerpiece, the insulator. That doesn't matter so much if it's still connected. It's not a good thing because it's supposed to dissipate heat. However, I don't imagine that that thing gets very hot. I can check it later, and we can check this one and see how hot they get. I'm thinking more that it's a mechanical problem. It got banged or hit or something somewhere when somebody was working on it, probably this thing here because it's in the same area, and broke the insulator, probably broke the connection, and the technician probably just spot soldered the end of the coil back to the terminal. That's okay. If we have to replace it, we'll try to find a replacement of the same value with the same wire round rating. Not the easiest thing to do. But we can tell if that piece of coil is connected the same way we checked the coils here with the center tap approach. So let's start with the side we know is most likely good.
And we got jumping all over the place because I can't make a good connection on it. Yeah, it might be better. Okay, we got 0.8 ohms to here. Hold on. I probably should have done this from the get-go. That doesn't sound very promising. And that could just be that wire that's in series with it there. I just put some leads on my probe, so let me go ahead and zero this out. Okay. So we'll clip that on there, which will give us a much better reading than my hands. Okay, we got 0.2 ohms. That's 0.1. Now we got a dead short from there to there. And that might be those two wires. There's one connected here, there's one connected here, and they're coiled together and they go that way. Well no, we still shouldn't have that low of a volt of a resistance. Oh, there's a wire here on the center tap. See it? It goes over to here. If this wire is going to a coil and this wire here is going to a coil, then yes, we would be reading, just like reading across this, we'd be reading across the coil and not the resistor. That remains to be seen. Let's go from this side, which is the damaged area, to the center and see if we get some kind of a reading. If that's the case, what I just mentioned, then we won't get nothing valuable here either. And then with the same problem, 0.2 ohms, which is probably a dead short. So that resistor, I can't visually tell. I have to get a lot closer, and the camera's in my way to do that, to see if this is physically connected to this side. I'm thinking it's not. I'm thinking there's damage here. And if there is, then we'll just take this out and we'll put a new wire around resistor across here, or two. One that goes halfway for the center tap and one that goes the rest of the way, and we can pull the values from the schematic when I get the schematic. Okay, so let's continue. I'm going to leave these clips on here just because it might make it easier on this board. The next thing we want to check, and actually let's check this capacitor across the circuit here to ground before we go any further. Might not know anything, but it's worth a shot. Okay, there's nothing. That's good. That capacitor is not shorted at least. All right, I'm going to turn the camera so you can see the board, and I'll have to raise it back up a little. Maybe I can just do that here. Move the camera to a better spot. Set some light down there. That helps if that'll stay there. We're going to check those resistors there. So we'll start with this one, which is green, black, yellow. So that's a 10 meg. Oh, what do you mean? 10 meg should be. The other side of it looks like there. Oh, it's 1 meg, I'm sorry. And it's reading 800. It's just barely in spec. That's orange. Yellow, 4 zeros, still 1 0, 4 zeros, and green, so it's 1 meg. Oh, that's something not right. 500K, and I'm reading 778K. Yeah. I'm having trouble with that this morning. Because I'm used to 1 meg ohm resistance, that's why I'm having trouble with this. Throwing my mind off. We got 5, a 0, and 4 more zeros, so that's 5 zeros. So that would be 5 zeros is 100,000, so that's 500,000. And I'm getting 774,000. So that resistor is most likely damaged, or I'm connecting to the wrong place and reading two resistors. I don't know, it looks like I'm in the right place. Well, we'll find out when I check that one behind it, which is 4, 0, and 3 resistors, 3 zeros. So 40K. Getting in there is not going to be easy. Maybe you can touch that read in there. I'm getting 63K. So this board, we're definitely going to have to do some work here. And again, I'm assuming that this is in the right place, but it sure looks like it. Yeah, I would say that's the right place. Yep. Okay. And the next connection is here. It's just hard to see. There's so many capacitors and things in the way over there. The next one is here. And clip there. And now I'm looking at this one, which is 5, same as this one. 5, 0, and 4 zeros. 500. Okay, let me see, what can I get in that? Maybe I can get to the end. I'm going to click on it. Can't get to the wire that way. It's one capacitor, it's right in the way. Oh, it's soldered there. I thought it was just this side's on a floating wire. I thought that was too. Okay, I think I'm going to buy it now. 732K. It's supposed to be 500K. So these two are bad. Unless there's something I'm not seeing and that's adding to it, but no, it shouldn't be. Okay, these are easier to get to, so let's check these. That looks like brown, black, and 4 zeros, so that would be 100K. And we can measure that one over here. This is my alligator clip bag on here. And we got 115K, so it's still within tolerance. Leave that one there, measure the next one, which is here. It's the same value, 133K, so that one's bad. This one's okay, this one's bad. Now we'll try those 200Ks down here in these red ones. Let me try this one first. This is my halfway point. I got 275K, that's bad. Which I figured these would be out. These are the power, this is the power circuit. It has a lot of draw on it, and with the bad capacitors on the power line, the B plus line, it would have pulled those out. That one in the back is 250K, it's out of spec too, it can't be more than 240. So those have got to be changed. And then can you see this bottom one? Bring it down a little bit more, I think you can see it. Maybe not. Oh, sorry about that. Lock it in here. So you might not be able to see that because of the angle. There's one here. And I can't tilt the camera that angle. So let me check it. It's orange, black, red. So it would be 3K ohm. And it's reading nothing because my alligator clip came off. 3.8. So it's bad. It can't be over 3600. It's 3800. So it's got to be changed. Everyone on that board is bad. Well, I say bad. They're out of tolerance. The radio would work with them, but they're out of tolerance. So you just seen the process of going through, checking resistors, checking capacitors for shorts. I didn't check them all, but I give you an idea, and how to check resistors in circuit. And remember, some of them that are close and a little bit out of tolerance, when you take them out of circuit, they may be fine. It could just be something else in the circuit that's with it. But most of the time, you can check them in circuit without a problem. So that'll help some of y'all at the beginning, and most of you already know that. I'm sorry for boring you to tears with the process, but I create these videos to try to help young people or new people in the trade, whether they're doing it as a hobby or learning tubes as a profession, and to expand their knowledge of maybe from solid state to tube history. You know, I want to be precise to help people understand exactly what's going on and how to go through and check the components. One thing that this does help me know is that there's a very good chance that, discounting of course that these things are wired correctly, I mean, I don't know, I haven't checked that, but aside from the work that's been done to it, the original components, there's a very good chance that this unit will work fine even without this resistor being here. It would still work fine. It may not be perfect, but it would work. The other thing is I've ruled out for a good percentage of risk of a dead short that would cause a problem and drive the current up. Of course, I'm already going to be checking the current when I use my current limiting bulb and kilowatt meter. You know, on a variac, I'm going to monitor the current as I bring the voltage up to the unit. But I already know that the risk of a short, at least for the initial turn on, the risk of a short is very low, and that's a good thing, because I'm not going to bring it right on with 120 volts. I'm going to bring it up slowly at 50 volts and gradually work up to 110 volts, which is what this was originally designed for. Okay, the other thing we can check is the potentiometers here and see the volume controls and see if they're working.
Again, I probably should have left my clips on to get in there. It just helps when you can, on these old solder joints, even though the solder joints are mechanically good and the electrical connection between the joint and the wire that's soldered to it is good because it goes into the solder, the outside of the solder gets oxidized and that gives it this gray color. And so when you're trying to hold the probe on it, the meter will fluctuate all over the place because you're not getting a true connection. When you use alligator clips, they actually bite through the coating that's, see how, I don't know if you can see that, but they bite through the coating of the solder and actually get a better connection. So like here, see how you can see the shiny spot where the clip hits? It actually cuts through. So can you see this? Yeah, you can see that. Okay, we're going to check this potentiometer. I don't know if it's a tone control, volume control, what it is. Fine tuning, who knows? Well, we don't care. We just want to know that it's got a value when you turn it. So we go from one side to the center pole and turn okay, now we're getting something. It kind of gave me a scare there. Okay, and the switch is working. All right, so that goes across the switch. Let's go back to our center tap here. The other side of the volume control has no wire attached, so we don't need to worry about it. And I'm getting a reading. Yay. 24K, 80K, I'm turning it quite a bit, 160K, 250K. Great, the volume control is fine, and it goes up to 560K. It's still counting up, that's strange. It might be a capacitor across it charging too. Yeah, let's see where it stops at. 569. All right, 570K. Once the capacitor charges beyond the resistance of the potentiometer, it'll stop counting. It'll stop counting because the resistance is less than the resistance of the capacitor charging is going to show the resistance. So it's a 170K ohm potentiometer, and it's working fine. We'll continue. Thanks for watching. I'll consider this part one. This video is running long, and I'll surely shorten it down. But I wanted to give you a view of this and help you to see how you go through checking the components. Chassis side. Top side we haven't done the tubes, but you see what we're doing. Thanks for watching.